This episode is brought to you by Cisco Educational Premium. For ages, it has been said that mathematics is the mother of all sciences. All the concepts of science stem from mathematics. This alma mater, the nourishing mother, mathematics is truly astounding. And what better concept to demonstrate this than the birth of light as a consequence of solving Maxwell's equations. Maxwell's equations are 4 in number. The first is the Gauss law for electricity, which relates the net electric flux to the net enclosed charge. The second is the Gauss law for magnetism, which relates net magnetic flux to the net enclosed charge. The third is the Faraday's law, which relates induced electric field to the changing magnetic flux. And the last but not the least is the Ampere-Maxwell law, which relates induced magnetic field to the changing electric flux and to the current. But wait, Caleb. What they call Maxwell's equation again? That's a story for another day. Now, the real deal. This is a math show. We're not going to just make sense of statements, but crucially piece together reality from numbers, from mathematics. No shortcuts. These are Maxwell's equations in their differential form. In a vacuum, when there are no electric charges and currents, our Maxwell's equations will evolve to as shown. Our equations are now simpler. The first and the second equations are the divergence of electric and magnetic fields. These two are telling us that if there are no charges present to create magnetic and electric field lines or terminate them, there will be no divergence. The fields will be continuous. They will not start or end. Astonishingly, Maxwell's equations, even in completely empty space, can define and allow the existence of magnetic and electric fields. The other two equations deals with how these continuous electric and magnetic fields behave. The third tells us that the electric field can be created by firings of magnetic fields in the vicinity. Same as the third, the fourth equation tells us that we can get some magnetic fields in the vicinity by firings of magnetic fields. Both of these fields must be at right angles to one another for one of these fields to generate the other. Say in the third equation as shown. Remember mathematically, the left hand side of this equation, del cross E, we are taking the curl of this. We are taking the cross product. Any factors within the cross product will always be completely at right angles to the resultant factors, which in our case is the magnetic field. So if the electric field points anywhere in the xy plane, the magnetic fields must be at right angles to it. The same thing goes for the fourth equation. Any change in the electric field causes new magnetic field at right angle to the electric field. Remember, we are solving Maxwell's equations. Now I want to find electric and magnetic fields formulas, so that when we substitute the left hand side, it will match the right hand side of these equations. We want the third and second equations. Remember, we can't get information about electric field without knowing the value of the magnetic field, and we can't get any information about the magnetic field if we do not know the value of the electric field. So what gives? These equations seem to be conjoined and tangled, so to speak. In math talk, we can say that it is a first order coupled differential equation. What we want to do is to decouple these equations so that they will be completely separate equations. A separate equation for E and a completely separate equation for B. Decoupling them, so to speak. Now, let us start with the fourth equation. Let us take the curl of both sides of this equation, and so we get as shown. On the left side, let us use the factor identity, so we get as shown. On the right hand side, let us exchange the order of the derivatives. Now replacing del cross E using the third Maxwell's law, we get as shown. Now combining everything, if you didn't notice, we have successfully decoupled the two equations into a second order linear partial differential equation. Just to review, the left hand side is the Laplacian operator, del square B, which is a factor 2, same as the right hand side, ignoring mu naught and epsilon naught, we have as shown. And so since both sides are factor quantities, the x component of the left hand side must match that on the right hand side. The y components must match too. Same goes for z. Just to remember, we are now finding the solutions to the second order decoupled differential equation. As we had seen, these really three separate equations. One for x, one for y, and one for z. Now we are going to try some functions on how they will solve our equations. Not that we are trying trial solutions for the x component, which is just the same for the y component, and so for the z component. Now I want to look for a function f that might obey the equation as shown, with alpha just a constant. Say partial sub t square f was just proportional to the original f, and similarly for partial x square f, we want to look for a function whose second derivative is equivalent to the original function apart from e to the x, so to say. Can you remember any? Yes, any cosine or sine function fit here. Partial t square cos t is equivalent to negative cos t. We are going to allow for f to have both an amplitude and frequency. F is equivalent to a cos omega t, where we have omega to be the angular frequency in radians per second. So if we have partial x square bx to be as shown, and if both partial x square bx and partial t square bx are proportional to bx, then we are on the right track. We know that partial x square a cos omega t is equivalent to 0. So we need to add some spatial dependence, some x, so to speak. We are going to propose an ansatz, a trial solution, so to speak. For those who took differential equations classes, I know this word, ansatz, when on top of our heads. It's just an example solution, a trial solution. The product of a function that depends only on space times a different function that depends only on time. Looks like the good old chain rule is in our favor. If partial x square fx is proportional to fx and partial t square gt is proportional to gt, that is, they are sine and cosines, then we have partial x square bx as shown. Also, partial t square bx as shown. And so we see that partial x square bx is proportional to partial t square bx, which is exactly what we need. Now let us consider these two functions, our separable solutions. F is the frequency that is waves per seconds. K is the number of waves per meter. You can think of Kx as the spatial frequency analogous to Ft, which is the time frequency. Now calculating the derivatives of our two functions. we have partial x square fx and partial t square gt as shown. And so if our magnetic field is expressed as bxxt as shown, provided by our ansatz, then we have partial x square bx and partial t square bx as shown. But let's just check. Our guess bxxt is as shown with partial x square bx to be as shown. So it's okay. And so now we need to ask ourselves, does this obey the second order linear partial differential equation resulting from Maxwell's equations? Is partial x square bx as shown? Now replacing partial x square bx and partial t square bx with the expressions as shown, but the left must match the right. So cancelling terms we get as shown. And so the question we need to ask, does our ratio match the actual numbers of mu naught epsilon naught and the units? Then those are the exact functions that are gonna solve Maxwell's equations. Now let us just look at the units of the ratio f on k as shown. This means that our f on k represents a velocity. Isn't it incredible? And so letting f on k be equivalent to v, then our equation will be satisfied when f on k square is equivalent to v square, which is equivalent to 1 on mu naught epsilon naught. Then what is the exact value of v? We know that mu naught is the permeability of free space, a magnetic constant, and it has a defined value. And epsilon naught is a dielectric permittivity of free space, and it too has a determined value. And so we are able to find the value of v, and we find it to be 2.998 times 10 raised to 8 meters per second, which is what? Which is the speed of light. This is the solution to the Maxwell's equations. The speed of light is the solution to the Maxwell's equations. The only solutions to Maxwell's equations have the property that they propagate at the speed of light, which are combination of magnetic fields and electric fields orthogonal to one another, carrying with them energy at that specific velocity, which is the speed of light or any electromagnetic radiation specifically. It is not only light that travels at that speed, all electromagnetic radiation specifically. And so James Clerk Maxwell created light mathematically. Whether this was just a coincidence or a deliberate attempt, it doesn't matter. What matters is that it is correct. This episode is brought to you by Cisco Educational Premium. The atom is the basic building block of matter around us. Your body, your clothing, your chair, your bed, even the device you're watching this video on is made of atoms. The idea of the atom is basically the reason why chemistry exists. The periodic table of elements is basically built on atoms. Ever since the idea of the existence of atoms was put forward by the philosopher Democritus, who said that the universe is made of atoms and the void in which they exist. This idea was since given a solid grounding by scientists, particularly chemists and physicists, proving its existence by scientific method. Today, there is solid evidence that atoms exist. And when we say that atoms exist, we really do know what we are talking about. An atom is most efficient as a dense and compact nucleus encircled by orbitally moving orbiting electrons. This concept naturally raises the question, how do
electrons sustain their motion around the nucleus without slowing down? This question became a major concern in the early 20th century and led to the development of quantum mechanics itself. During this time, physicists were making strides in understanding atoms and recognized that each atom contained a positively charged nucleus with a considerable mass surrounded by 10 negatively charged electrons. Armed with this general understanding, they sought to construct a more detailed model. Initially, scientists drew inspiration from the solar system with a dense nucleus, the sun orbited by smaller particles, the planets. However, this model posed two significant issues. First, charged particles that accelerate must emit electromagnetic radiation by observations, at least by Maxwell's equations. Since electrons are charged and accelerate during their orbits, they should emit radiation which will cause them to lose energy and quickly spiral inward into the nucleus. However, atoms are known to exist far much longer than a picosecond, making this model incorrect. Secondly, atoms were observed to emit radiation at specific frequency, unlike the continuous emission expected from an electron following the solar system model. Niels Bohr, a renowned Danish physicist, was the first to propose a solution to these problems. In 1913, he suggested that electrons in an atom do not just occupy, just inhabit, but confined to specific distances from the nucleus. He also proposed that there was a minimum distance an electron could reach beyond which it could not move any closer to the nucleus. Those ideas were not just mere speculations. They were built on the work of German physicist Max Planck, who had proposed the quantization of radiation emission a little over a decade. According to Planck, objects could only absorb or emit radiation in discrete chunks, not in any arbitrary value. These discrete chunks were characterized by constant value known as Planck's constant, which had units akin to angular momentum. Bohr adopted this concept and applied it to electrons orbiting a nucleus. He asserted that the smallest possible orbit of an electron would have an angular momentum equivalent to 1 Planck constant. Higher orbits would have integer multiples of the Planck's constant, such as twice or 3 times its value, but never fractions like half or 2 and 3. The full comprehension of why electrons possessed specific orbits and well-defined levels required the more complete development of quantum mechanics. Electrons, like other matter particles, exhibit both particle and wave behavior. While we might envision an electron as a tiny planet orbiting the nucleus, we can usually visualize it as a wave enveloping a nucleus. Waves confined within a limited space must adhere to specific rules. They cannot have arbitrary wavelengths. Instead, they must consist of standing waves that fit precisely within the space. This analogous to playing a musical instrument. When you fix the ends of a guitar string, only specific wavelengths produce distinct notes. Similarly, the electron wave circling a nucleus must fit the available space, and the nearest orbit is determined by first standing wave of that electron. Future advances in quantum mechanics would continue refining this model, but the fundamental point remains unchanged. An electron cannot approach the nucleus any closer due to its inherent quantum mechanical constraints, which prevent it from occupying smaller space. However, an entirely different approach to understand this situation do not rely on quantum mechanics at all. Instead, it considers the various energies involved. An electron in orbit around the nucleus experiences electrical attraction towards the nucleus, constantly being pulled closer. At the same time, possesses kinetic energy trying to propel it away from the nucleus. For a stable atom, these two forces are in equilibrium. In fact, the total energy of an electron in orbit, which combines its potential and kinetic energies, is negative. Consequently, adding energy to the atom is necessary to remove an electron. This concept parallels the behavior of planets orbiting the Sun. To remove the planet from the solar system, energy must be added to the system. One way to envision this scenario is to picture an electron falling inwards towards the nucleus due to the attractive electric charge. However, because of the principle of quantum mechanics, the electron can never reach the nucleus, becoming perpetually in a stable orbit. Nevertheless, this situation is permissible according to physics because the total energy of the system is negative, signifying its stability and binding components together to form a long-lasting atom. Everything around us is composed of atoms. All the matter in the observable universe is estimated to be more than 10 quadrillion quintillion. This number is 1 followed by 78 zeros. Atoms are tiny particles consisting of electrons, protons and neutrons, which are in turn made up of quarks. The origin of these particles that make up atoms can be traced to the Big Bang. The Big Bang theory explains the beginning of the universe, where an immense amount of energy condensed, leading to the formation of atoms. There are more technical details than this, which we are going to look at them. To understand the scientific perspective of the Big Bang, we need to examine the events of the early universe. Unfortunately, we do not have a definitive understanding of precisely when the universe started, or if it indeed started at all. Our base model, the Standard Model of cosmology, allows us to trace back time close to the beginning, but we encounter a barrier at t is equal to 1. This theory predicts a singularity, a moment of infinite density where all matter and energy were compressed into an infinitely small point. Most physicists predict that this prediction may not be entirely accurate. We can only go back to one Planck time, which is about 10 raised to negative 43 seconds. Before this, we have no knowledge of what occurred both by observation and mathematics. So while we get very close to the beginning, it is not precisely at t is equal to 1. Understanding the events of this incredibly small time scale requires a quantum theory of gravity, where gravity, which explains the behavior of large objects, meets quantum mechanics, which governs the behavior of particles at tiny scales. This episode is brought to you by Cisco Educational Premium. Did you know that Planck units are units of measurement? In particle physics and physical cosmology, Planck units are a set of units of measurement defined exclusively in terms of 4 universal physical constants, in such a manner that these physical constants take on the numerical value of 1 when expressed in terms of these units. Originally proposed in 1809 by German physicist Max Planck, these units are a system of natural units because their definition is based on properties of nature, more specifically the properties of free space, rather than a choice of prototype object.
They are relevant in research on unified theories such as quantum gravity. The term Planck scale refers to quantities of space-time energy and other units that are similar in magnitude to corresponding Planck units. This region may be characterized by particle energies of around 10 raised to 19 gigavolts or 10 raised to 9 joules. Time intervals of around 10 raised to negative 43 seconds and lengths of around 10 raised to negative 35 meters, approximately the energy equivalent of the Planck mass, the Planck time, and the Planck length respectively. At the Planck scale, the predictions of the Standard Model, quantum field theory, and general relativity are not expected to apply, and quantum effects of gravity are expected to dominate. The best known example is represented by the condition in the first 10 raised to negative 43 seconds of our universe after the Big Bang, approximately 13.8 billion years ago. The four universal constants that by definition have a numerical value of 1 when expressed in these units are 1. The speed of light in a vacuum c. 2. The gravitational constant g. 3. The reduced Planck constant h. And 4. The Boltzmann constant k sub b. Planck units do not incorporate an electromagnetic dimension. Some authors choose to extend the system to electromagnetism by, for example, adding either the Coulomb constant k sub b is equivalent to 1 on 4 pi E naught or electric constant E naught to this list. Similarly, authors choose to use variants of the system that give other numerical values to one or more of the four constants we have seen. Any system of measurement may be assigned a mutually independent set of base quantities and associated base units, from which all other quantities and units may be derived. In the International System of Units, for example, the SI base quantities include length with associated unit of the meter. In the system of Planck units, a similar set of base quantities and associated units may be selected, in terms of which other quantities and coherent units may be expressed. The Planck unit of length has become known as the Planck length, and the Planck unit of time is known as Planck time, but this nomenclature has not been established as extending to all quantities. All Planck units are derived from the dimensional universal physical constant that define the system, and in a convention in which these units are omitted, that is treated as having dimensionless value 1. These constants are then eliminated from equations of physics in which they appear. For example, Newton's law of universal gravitation. Of course, these Planck constants appear, so they are eliminated as shown by the second equation. Both equations are dimensionally consistent and equally valid in any system of quantities, but the second equation with G absent is relating only dimensionless quantities, since any ratio of two like-dimensioned quantities is a dimensionless quantity. If by shorthand convention it is understood that each physical quantity is the corresponding ratio with a coherent Planck unit, or an I-quad expressed in Planck units, the ratios we have seen may be expressed simply with the symbols of physical quantity without being scaled explicitly by their corresponding unit. This last equation without G is valid with F prime, M1 prime, M2 prime, and R prime, being the dimensionless ratio quantities corresponding to the standard quantities written, for example, F prime being F or F prime being F1, F3, but not as a direct equality of quantities. This may seem to be like what setting the constant Cg, etc.,
to 1 if the correspondence of the quantities is thought of as equality. For this reason, Planck or other natural units should be employed with care, referring G is equivalent to C is equivalent to 1. Paul S. Wesson wrote that mathematically it is an acceptable trick which saves labor. Physically, it represents a loss of information and can lead to confusion. The concept of natural units was introduced in 1874 when George Johnston Stoney noted that electric charge is quantized. Derived units of length, time, and mass now are named Stoney units in his honor. Stoney chose these units so that G, C, and the electron charge E would be numerically equal to 1. In 1899, 1 year before the advent of quantum theory, Max Planck introduced what became later known as Planck constant. At the end of the paper, he proposed the base units that were later named in his honor. The Planck units are based on the quantum of action, now usually known as the Planck constant, which appear in the Wien approximation for black-body radiation. Planck underlined the universality of the new unit system, writing, "It is possible to set up units for length, mass, time, and temperature, which are independent of special bodies or substances, necessarily retaining their meaning for all times and for all civilizations, including extraterrestrial and human ones, which can be called natural units of measure." Planck considered only the units based on the universal constants GH, C, and KB to arrive at natural units for length, time, mass, and temperature. These definitions differ from the modern ones by a factor of √2 pi, because the modern definitions use reduced Planck's constant rather than Planck constant. Unlike the case with the International System of Units, there is no official entity that establishes a definition of a Planck unit system. Some authors define the base Planck units to be those of mass, length, and time, regarding an additional unit for temperature to be redundant. Other tabulations add, in addition to a unit of temperature, a unit for electric charge, so that either the Coulomb constant Ke or the vacuum permittivity E0 is normalized to 1. Thus, depending on the author's choice, this charge unit is given. Some of these tabulations also replace mass with energy when doing so. The Planck charge, as well as other electromagnetic units that can be defined like resistance and magnetic flux, are more difficult to interpret than Planck's original units and are used less frequently. In SI units, the values of CH, E, and KB are exact, and the values of E0 and G in SI units respectively have relative uncertainties of 1.5 times 10 raised to negative 10 and 2.2 times 10 raised to negative 5. Hence, the uncertainties in the SI values of the Planck units derive almost entirely from uncertainty in the SI value of G. Compared to the Stoney units, the Planck base units are all 1 on root alpha, approximately 11.7 times larger. In any system of measurement, units for many physical quantities can be derived from base units. The table offers a sample of derived Planck units, some of which are seldom used. As with the base units, their use is mostly confined to theoretical physics because most of them are too large or too small for empirical or practical use, and there are large uncertainties in their values. Some Planck units, such as those of time and length, are many orders of magnitude too large or too small to be of practical use, so that Planck units as a system are typically only relevant to theoretical physics. In some cases, a Planck unit may suggest a limit to a range of physical quantity where present-day theories of physics apply. For example, our understanding of the Big Bang does not extend to the Planck epoch. That is, when the universe was less than 1 Planck time old. Describing the universe using the Planck epoch requires a theory of quantum gravity that will incorporate quantum effects into general relativity. Such a theory does not yet exist. Several quantities are not, and I quote, extreme in magnitude, such as the Planck mass, which is about 22 micrograms, very large in comparison with subatomic particles and within the mass range of living organisms. Similarly, the relative units of energy and momentum are in the range of some everyday phenomena. Planck units have little anthropocentric arbitrariness, but do still involve some arbitrary choices in terms of the defining constants. Unlike the meter and second, which exist as base units in the SI system for historical reasons, the Planck length and Planck time are conceptually linked at a fundamental physical level. Consequently, natural units help physicists to reframe questions. Frank Wilczek puts it succinctly. We see that the question is not why is gravity so feeble, but rather why is the proton's mass so small? For natural Planck units, the strength of gravity simply is what it is, a primary quantity, while proton's mass is the tiny number 1 on 13 quintillion. While it is true that the electrostatic repulsive force between two protons alone in free space greatly exceeds the gravitational attractive forces between the same two protons, that's not about the relative strength of the two fundamental forces. From the point of view of Planck units, this is comparing apples with oranges because mass and electric charge are incommensurable quantities. Rather, the disparity of magnitude of force is a manifestation of the fact that the charge on the proton is approximately the unit charge, but the mass of the protons is far less than the unit mass. In particle physics and physical cosmology, the Planck scale is an energy scale around 1.22 times 10 raised to 19 gigafolds. The Planck energy corresponding with the energy equivalent of the Planck mass is 2.17645 times 10 raised to negative 8 kilogram, at which quantum effects of gravity become significant. At this scale, present description and theories of subatomic particle interactions in terms of quantum field theory break down and become inadequate due to the impact of the apparent non-renormalization of gravity within current theories. At the Planck scale, the strength of gravity is expected to become comparable with the other forces, and it has been theorized that all the fundamental forces are unified at that scale. But the exact mechanism of this unification remains unknown. The Planck scale is therefore the point at which the effects of quantum gravity can no longer be ignored in other fundamental interactions, where current calculations and approaches begin to break down and a means to take account of its impact is necessary. On these grounds, it has been speculated that it may be an appropriate lower limit at which a black hole could be formed by collapse. While physicists have a fairly good understanding of the other fundamental interactions of forces on the quantum level, gravity is problematic and cannot be integrated with quantum mechanics at very high energies using the usual framework of the quantum field theory. At lesser energy levels, it is usually ignored, while for energies approaching or exceeding the Planck scale, a new theory of quantum gravity is necessary. Approaches to this problem include string theory and M theory, loop quantum gravity, non-commutative geometry, and causal theory. In Big Bang cosmology, the Planck epoch or the Planck era is the earliest stage of the Big Bang before the time passed was equal to the Planck time, or approximately 10 raised to negative 43 seconds. There is no current available physical theory to describe such short times, and it is not clear In what sense the concept of time is meaningful for value smaller than the Planck time? It is generally assumed that quantum effects of gravity dominate physical interactions at this time scale. At this scale, the unified force of the Standard Model is assumed to be unified with gravitation. Immeasurably hot and dense, the state of the Planck epoch was succeeded by the Grand Unification epoch, where gravitation is separated from the unified force of the Standard Model, in turn followed by inflationary epoch, which ended after about 10 raised to negative 2 seconds, or about 10 raised to 11 Planck time. After the measurement of the cosmological constant in 1998, estimated at 10 raised to negative 122 in Planck units, it was noted that this is suggestively close to the reciprocal of the age of the universe squared. Barrow and Shaw propose a modified theory in which the cosmological constant lambda is a field evolving in such a way that its value remains lambda equivalent to the age of the universe squared through the history of the universe. The Planck length, denoted L3, is a unit of length defined as Lp is equivalent to root of reduced Planck constant G on C raised to 3. It is equal to 1.6162518 times 10 raised to negative 45 meters, where the two digits enclosed by parentheses are estimated standard error associated with the reported numerical value, or about 10 raised to negative 20 times the diameter of a proton. It can be motivated in various ways, such as considering a particle whose reduced Compton wavelength is comparable to its Schwarzschild radius. Though whether those concepts are in fact simultaneously applicable is open to debate. The same heuristic argument simultaneously motivates the Planck mass. The Planck length is a distance scale of interest in speculation about quantum gravity. The Bekenstein-Hawking entropy of a black hole is 1/4 area of its event horizon in units of Planck length squared. Since 1950s, it has been conjectured that quantum fluctuations of the space-time metric might make the familiar notion of distance inapplicable below the Planck length. This is sometimes expressed by saying that, and I quote, space-time becomes a form at the Planck scale. It is possible that the Planck length is the shortest physically measurable distance, since any attempt to investigate the possible existence of shorter distances by performing high energy collision will result in a black hole production. High energy collision, rather than splitting matter into finer pieces, would simply produce bigger black holes. The strings of string theory are modeled to be on the order of the Planck length. In theories with large extra dimensions, the Planck length calculated from the observed value of G can be smaller than the true fundamental Planck length. The Planck time, Tp, is the time required for light to travel a distance of 1 Planck length in a vacuum, which is a time interval of approximately 5.39 times 10 raised to negative 44 seconds. No current physical theory can describe time scale shorter than the Planck time, such as the earliest events after the Big Bang. Some conjecture that the structure of time need not remain smooth at intervals comparable to the Planck time. The Planck energy EP is approximately equal to the energy released in the combustion of the fuel in automobile fuel tank, 57.2 liters at 4.2 megajoule per liter of chemical energy. The ultra energy cosmic ray observed in 1991 had a measured energy of about 50 joules, equivalent to about 2.5 times 10 raised to negative 8 Planck energy. Proposal for theories of doubly special relativity posit that in addition to the speed of light, an energy scale is also invariant for all inertial observers. Typically, this energy scale is chosen to be the Planck energy. The Planck unit of force may be thought as the derived unit of force in the Planck system. if the Planck units of time, length, and mass are considered to be the base units. It is the gravitational attractive force of two bodies of one Planck mass each that are held one Planck length apart. One convention for the Planck charge is to choose it so that the electrostatic repulsion of two objects with Planck charge and mass that are held one Planck length apart balances the Newtonian attraction between them. Some others have argued that Planck force is on the order of the maximum force that occurs between two bodies. However, the validity of these conjectures has been disputed. The Planck temperature Tp is 1.41678416 times 10 raised to 32 Kelvin. At this temperature, the wavelength of light emitted by thermal radiation reaches the Planck length. There are no known physical models able to describe temperatures greater than the Planck temperature. A quantum theory of gravity would be required to model the extreme energies attained. Hypothetically, a system in thermal equilibrium at the Planck temperature might contain Planck scale black holes, constantly being formed from thermal radiation and decay via Hawking evaporation. Adding energy to such a system might decrease its temperature by creating larger black holes whose Hawking temperature is lower. Physical quantities that have different dimensions such as time and length cannot be equated even if they are numerically equal. Like 1 second is not the same as 1 meter. In theoretical physics, however, this problem may be set aside by a process called non-dimensionalization. The effective result is that many fundamental equations of physics, which often include the sum of the constants used to define Planck units, become equations where these constants are replaced by 1. Examples include the energy momentum relation becomes E square is equivalent to C square bracket all of that raised to 2 plus PC square, which become E square is equivalent to M square plus P square, and the Dirac equation which evolved, which becomes as shown. As we have already looked at, Planck units are derived by normalizing the numerical values of certain fundamental constants to 1. These normalizations are neither the only ones possible nor necessarily the best. However, the choice of what factors to normalize among the factors appearing in the fundamental equation of physics is not evident, and the values of Planck units are sensitive to this choice. The factor 4 pi is ubiquitous in theoretical physics because in three-dimensional space, the surface area of a sphere of radius r is 4 pi r square. This, along with the concept of flux, are the basis for the inverse square law, Gauss law, and the divergence operator applied to the flux density. For example, gravitational and electrostatic fields produced by point objects have spherical symmetry, and so the electric flux through a sphere of radius r around a point charge will be distributed uniformly over that sphere. For this, it follows that a factor of 4 pi r square will appear in the denominator of Coulomb's law in rationalized form. Both the numerical factor and the power of the dependence on r would change if space were higher dimensional. The correct expression can be deduced from the geometry of higher dimensional spheres. Likewise, for Newton's law of universal gravitation, a factor of 4 pi naturally appears in Poisson's equation when relating the gravitational potential to the distribution of matter. Hence, a substantial body of physical theory developed since Planck's 1899 paper suggests normalizing not g but 4 pi g or 8 pi g to 1. Doing so introduced a factor of 1 on 4 pi or 1 on 8 pi into non-dimensionalized form of the law of universal gravitation, consistent with the modern rationalized formulation of Coulomb's law in terms of vacuum permittivity. In fact, alternative normalizations frequently preserve the factor of 1 on 4 pi in the non-dimensionalized form of Coulomb's law as well, so that the non-dimensionalized Maxwell's equation for electromagnetism and gravitoelectromagnetism both take the same form as those for electromagnetism in SI, which do not have any factors of 4 pi. When these apply to electromagnetic constants E naught, this unit system is called, and I quote, rationalized. When applied additionally to gravitation and Planck units, these are called rationalized Planck units and are seen in high energy physics. The rationalized Planck units are defined so that C is equivalent to 4 pi g, which is equivalent to reduced Planck's constant, which is equivalent to E naught, which is equivalent to Kb, which is equivalent to 1. There are several possible alternative normalizations. In 1899, the Newton's law of gravitation was still seen as exact, rather than as a convenient approximation, holding for an accord small velocities and masses. The approximate nature of Newton's law was shown following the development of general relativity in 1915. Hence, Planck normalized the gravitational constant g in Newton's law. In theories emerging after 1899, g nearly always appears in formulae multiplied by 4 pi, or a small integer multiplied thereof. Hence, a choice to be made when designing a system of natural units in which, if any, instances of 4 pi appearing in the equations of physics are to be eliminated for the normalization. 1. Normalizing 4 pi g to 1 and therefore setting g to be equivalent to 1 on 4 pi. Whose law for gravity becomes phi g, which is equivalent to negative 4 pi m in Planck units. Something else is that it eliminates 4 pi g from the Poisson equation. Also, it eliminates 4 pi g in the gravitoelectromagnetic GM equation, which hold in weak gravitational fields or locally flat spacetime. These equations have the same form as Maxwell's equations and the Lorentz force equation of electromagnetism, with mass density replacing charge density and with 1 on 4 pi g replacing epsilon naught. It normalizes the characteristic impedance Zg of gravitational radiation in free space to 1, normally expressed as 4 pi g on C. It also eliminates 4 pi g from the Bekenstein-Hawking formula for entropy of a black hole in terms of its mass, mbh, and the area of its event horizon, abh, which is simplified to SBH is equivalent to pi, ABH is equivalent to mbh square. 2. Setting 8 pi g to be equivalent to 1, and therefore setting g to be equivalent to 1 on 8 pi. This would eliminate 8 pi g from the Einstein field equations, Einstein-Hilbert action, and the Friedmann equation for gravitation. Planck units modified so that 8 pi g will be equivalent to 1 are known as reduced Planck units, because the Planck mass is divided by root 8 pi. Also, the Bekenstein-Hawking formula for the entropy of a black hole simplified to C-square educational premium is a section of C-square educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself, and I will see you in the next episode of C-Square Educationals.
Yeah.